NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will build a quadratic equation from symmetric information about its roots. Here is the problem. We are told that two numbers, call them x1 and x2, satisfy x1 squared plus x2 squared equals 5, and their product is 2. Our goal is to write the quadratic equation whose roots satisfy these relations, and to find all possibilities. For any quadratic with roots x1 and x2, the sum s equals x1 plus x2, and the product p equals x1 times x2. We will express the given information in terms of s and p. A very useful identity is that x1 squared plus x2 squared equals s squared minus 2p. Now substitute the numbers. We have 5 equals s squared minus 2 times 2. Therefore, s squared equals 9. So s can be plus 3 or minus 3. The product p is already given to be 2. To build the quadratic with a given sum and product of roots, we use the standard form x squared minus sx plus p equals 0. First case, s equals 3, and p equals 2 gives x squared minus 3x plus 2 equals 0. Second case, s equals negative 3, and p equals 2 gives x squared plus 3x plus 2 equals 0. Let us quickly verify by factoring. The first equation factors as x minus 1 times x minus 2 equals 0, so the roots are 1 and 2. The second equation factors as x plus 1 times x plus 2 equals 0, so the roots are negative 1 and negative 2. In both cases, the squares add to 5, and the product is 2. Final result. The possible quadratics are x squared minus 3x plus 2 equals 0, or x squared plus 3x plus 2 equals 0. Example. We will determine the coefficients a and b in the quadratic x squared plus ax plus b equals 0, given that the difference of the cubes of its roots equals 208. We will follow a structured, step-by-step plan using Vieta's relations and algebraic identities. Step 1. Let x1 and x2 be the roots. By Vieta's formulas, their sum s equals negative a, and their product p equals b. Step 2. Factor the difference of cubes x1 cubed minus x2 cubed equals x1 minus x2 times x1 squared plus x1 x2 plus x2 squared. Set this equal to 208. Step 3. Rewrite the quadratic part using s and p. The quantity x1 squared plus x1 x2 plus x2 squared equals s squared minus p. Step 4. The difference of the roots equals the square root of a squared minus 4b. That is, x1 minus x2 equals the square root of a squared minus 4b. Step 5. Substitute s equals negative a and p equals b. We obtain the square root of a squared minus 4. b times a squared minus b equals 208. Step 6. Factor 208 as 4 times 52 so that the square root term can be an integer. Set the square root of a squared minus 4b equal to 4. Then a squared minus 4b equals 16, and a squared minus b equals 52. Step 7. Solve the system. Subtract the first equation from the second. A squared minus b minus parentheses a squared minus 4, b equals 52 minus 16. That gives 3b equals 36, so b equals 12. Then a squared equals 52 plus 12, which is 64. Hence it equals plus or minus 8. Conclusion. The coefficients are a equals plus or minus 8 and b equals 12. These values satisfy the original condition that the difference of the cubes of the roots equals 208. Problem. For the quadratic equation x squared minus ax plus a minus 1 equals 0, determine the value of a that minimizes x1 squared plus x2 squared, where x1 and x2 are the roots. Step 1. Use the symmetric identity. For any quadratic with roots x1 and x2, the quantity x1 squared plus x2 squared equals the sum of roots squared minus 2 times the product of roots. Step 2. Read the sum and the product from the quadratic. 4x squared minus ax plus a minus 1 equals 0. The sum of the roots s is a, and the product of the roots p is a minus 1. Step 3. Substitute s equals a and p equals a minus 1 into the identity. Step 4. Simplify carefully. Distributing the negative 2 gives a squared minus 2 a plus 2. Note this is the tiny arithmetic correction compared to writing a squared minus 2 a plus 1. Step 5. Complete the square to see the minimum with respect to a. Write a squared minus 2 a plus 2 as left parenthesis, a minus 1 right parenthesis squared plus 1. Here is a quick graph of the function of a. The vertex occurs at a equals 1, and the minimum value is 1. Conclusion. The expression x1 squared plus x2 squared equals left parenthesis, a minus 1 right parenthesis squared plus 1. Therefore, its minimum is 1, achieved at a equals 1. Quick check, at a equals 1. The equation becomes x squared minus x equals 0, so the roots are 0 and 1. Then the sum of squares is 0 squared plus 1 squared equals 1, matching our minimum. In this lesson, we will solve a symmetric expression using Vieta's formulas. We are told x1 and x2 are the roots of the quadratic x squared minus 3x plus 1 equals 0. We want the value of x1 times x2 to the power negative 2 plus x2 times x1 to the power negative 2. To connect expressions in the roots to the coefficients, we use Vieta's formulas. For ax squared plus bx plus c equals 0 with roots x1 and x2, the sum s equals x1 plus x2 equals negative b over a, and the product p equals x1 times x2 equals c over a. In our problem, it equals 1, b equals negative 3, and c equals 1. So s equals 3, and p equals 1. Now we rewrite our target so that s and p appear naturally. Write x1 x2 to the power negative 2 as x1 over x2 squared, and similarly for the second term. Multiply each term by a clever form of 1. So both terms share the same denominator x1 squared x2 squared. Then the whole expression becomes x1 cubed plus x2 cubed divided by p squared. So we only need x1 cubed plus x2 cubed in terms of s and p. Use the identity for the sum of cubes in two variables. X1 cubed plus x2 cubed equals quantity s cubed minus 3ps. Substitute into our compact expression. It equals s cubed minus 3ps over p squared. Plug s equals 3 and p equals 1. That gives 27 minus 9 over 1, which equals 18. Therefore, the required value is 18. In this lesson, we will evaluate a symmetric expression in the roots of a quadratic. Our goal is to follow a clean, step-by-step path that mirrors a classic solution pattern. Suppose x1 and x2 are the roots of the equation 2x squared minus 3x minus 3 equals 0. We want the value of the quantity open. Step 1. Add the two fractions over a common denominator. Multiply top and bottom accordingly. Step 2. Expand the numerator terms. Step 3. Expand the denominator and group symmetric pieces. The denominator becomes 1 plus x1 plus x2 plus x1 x2. The numerator becomes x1 squared plus x2 squared plus 4 times x1 plus x2 plus 6. Step 4. Introduce the symmetric sums. Let s equal x1 plus x2 and p equal x1 times x2. Also recall x1 squared plus x2 squared equals s squared minus 2p. Substitute these into the fraction. Step 5. By Vieta's formulas for the quadratic 2x squared minus 3x minus 3 equals 0, s equals negative b over which is 3 halves, and p equals c over which is negative 3 halves. Step 6. Substitute s and p into the fraction we obtained. Step 7. Simplify. The denominator becomes 1 because plus 3 halves and minus 3 halves cancel. The numerator is 9/4 plus 6 plus 3 plus 6, which totals 69/4. Therefore, the value of the original expression is 69 over 4. Recap. Combine the fractions, group terms into symmetric sums s and p, replace x1 squared plus x2 squared by s squared minus 2p. Then use Vieta's formulas s equals 3 halves and p equals negative 3 halves. Substituting and simplifying yields 69 over 4. In this short proof, we use symmetric sums and Vieta's formulas. Given that alpha and beta are the roots of the quadratic x squared minus k, x minus k equals 0, show that alpha cubed plus beta cubed plus alpha cubed beta cubed is greater than or equal to 0. Step 1. From Vieta's formulas, we set s equal to alpha plus beta and p equal to alpha times beta. For our quadratic, S equals K, and P equals negative K. Step 2. Use the identity alpha cubed plus beta cubed equals S cubed minus 3PS. And alpha cubed beta cubed equals P cubed. Step 3. Adding these gives our target expression equal to S cubed minus 3PS plus P cubed. Step 4. Substitute S equals K, and P equals negative K. Step 5. The first and last terms, K cubed and negative K cubed, cancel, leaving 3K squared. Since K squared is always non-negative, the whole expression is at least 0, with equality only when K equals 0. To visualize non-negativity, here is the graph of y equals 3K squared. It lies on or above the horizontal axis for every real K, and only touches at the origin. Final result. The expression equals 3K squared, which is always non-negative. Example. We will find the value of m that makes the sum of the squares of the roots of a quadratic as small as possible. The quadratic is x squared plus open parenthesis 2 minus m close parenthesis x minus open parenthesis m plus 3 close parenthesis equals 0. Let x sub 1 and x sub 2 be the roots. By Vieta's formulas, the sum of the roots equals m minus 2, and the product of the roots equals negative of m plus 3. The sum of squares of two numbers equals the square of the sum minus 2 times the product. We will apply this identity to the roots. Substitute the expressions from Vieta, replace x1 plus x2 with m minus 2, and replace the product with negative m plus 3. Now simplify. Expand the square and distribute. Combine like terms to get a simple quadratic in m. To see the minimum clearly, complete the square. M squared minus 2m plus 10 equals open parenthesis, m minus 1 close parenthesis squared plus 9. A square is always non-negative, so the smallest value occurs when m equals 1, and the minimum sum of squares equals 9. Therefore, the optimal value is m equals 1, and the minimum possible value of the sum of squares of the roots is 9. In this lesson, we will prove a neat result about a quadratic with parameters m and n. Suppose m and n are natural numbers. If the roots of the quadratic x squared minus m times open parenthesis north plus 1 close parenthesis times x plus m plus n plus 1 equals 0 are natural numbers, then we will show that the product mn is at most 4. Let the roots be x1 and x2. By Vieta's formulas, the sum of the roots is m times open parenthesis north plus 1 close parenthesis, and the product of the roots is m plus n plus 1. Now we combine these two relations to craft a clever identity. Start by adding the product to the sum expression and rearrange terms. After grouping and factoring, we get n times open parenthesis, m minus 1 close parenthesis plus open parenthesis, x 1 minus 1 close parenthesis times open parenthesis, x2 minus 1 close parenthesis equals 2. This step is the heart of the proof. Because m, n, x1 and x2 are natural numbers, the two terms n times open parenthesis, m minus 1 close parenthesis, and open parenthesis x 1 minus 1 close parenthesis times open parenthesis x2 minus 1 close parenthesis are non-negative integers that add up to 2. There are only 3 possibilities for splitting 2 into a sum of 2 non-negative integers. Case A. Set n times open parenthesis, m minus 1 close parenthesis equals 0, and open parenthesis x 1 minus 1 close parenthesis times open parenthesis x2 minus 1 close parenthesis equal 2. Since n is natural, n equals 0 is impossible, so m minus 1 equals 0. Thus m equals 1. The factor 2 on the right can be realized by x1 minus 1 equals 1, and x2 minus 1 equals 2, giving x1 equals 2 and x2 equals 3 as natural roots. Using Vieta's product, 2 times 3 equals m plus n plus 1, so n equals 4. Therefore, m n equals 4. Case B, set n times open parenthesis, m minus 1 close parenthesis equal 1, and open parenthesis x 1 minus 1 close parenthesis times open parenthesis x2 minus 1 close parenthesis equal 1. The only way to get 1 as a product of naturals is n equals 1, and m minus 1 equals 1, hence m equals 2. The second product, equal 1, implies the roots are both 2. Check. Their sum is 4 and product is 4, which matches m equals 2 and n equals 1. Here, mn equals 2. Case C. Set n times open parenthesis, m minus 1 close parenthesis equal 2, and the other factorized term equals 0, which forces one root to be 1. For n times m minus 1 equal 2, the natural solutions are m equals 3 with n equals 1, or m equals 2 with n equals 2. In either situation, Vieta gives sum 6 and product 5, so the roots are 1 and 5. The products mn are 3 and 4, respectively. Collecting all possibilities, the product mn can be 2, 3, or 4, and in every case it does not exceed 4. Therefore, if the roots of the quadratic are natural numbers, the inequality mn less than or equal to 4 must hold. Example parameter pairs are m, n equals 2, 1, 1, 4, 3, 1, and 2, 2. Example: we will evaluate a to the power 1370 plus its reciprocal power, given that a squared plus a plus 1 equals 0. Step 1. Start from the given quadratic. Since a is not 0, divide both sides by a and factor. That gives a times the quantity a plus 1 over equals 0. Therefore, a plus 1 over equals negative 1. Step 2. From the quadratic, a squared equals negative a minus 1. Multiply both sides by a to get a cubed equals negative a squared minus. Substituting again gives a cubed equals 1. Note that a is not equal to 1 because it does not satisfy the original quadratic. Step 3. Because a cubed equals 1, the powers of a repeat every 3. Compute the remainder when 1370 is divided by 3. It is 2. Therefore, a to the power 1370 equals a squared. Step 4. The expression becomes a squared plus 1 over a squared. Use the identity, a plus 1 over a quantity squared equals a squared plus 2 plus 1 over a squared. Rearranging gives a squared plus 1 over a squared equals the square of a plus 1 over a minus 2. Step 5. Substitute a plus 1 over equals negative 1. Then the value is negative 1 squared minus 2, which equals negative 1. So the final answer is negative 1. Recap. From the quadratic, we found a plus 1 over a equals negative 1, and a cubed equals 1, which makes powers of a repeat every 3. Reducing the exponent gave a squared, and the identity for squares of sums finished the computation. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.